Good. So not many people know what is parameter shift rule. It's a rather niche topic, but actually nowadays you can find a lot of citations to this method because some people think that it's very promising suddenly. Unfortunately, my paper is showing the contradictory result. I don't think that it's promising actually. So.
Yes.
Yes, like this. So this is a table of content. It will be a problem statement. I will tell what is the parameter shift rule. Of course, you will see my new parameter shift rule. Actually, it would be two variations for well-posed problem and for ill-posed problem. I will tell, of course, what is it and what's the differences. And it will be a lot of different. There will be a lot of different examples of the specific Hamiltonian systems where the solution is exact. So this is a problem statement. You can see here a schematic plot of what is happening in variational quantum eigensolver, for example, or QAOA. These are the algorithms where you have some quantum machine here, and you insert inside of this quantum machine some set of parameters, some quantum thing is happening. And then you are doing some measurements here. Your measurements are, of course, expectation values of the observables that are serving you as estimates. So the function is actually illustrating the problem that you are solving. So you are combining these different expectation values, and all this combination I just denote as a function, for example. This is the result of your quantum algorithm. And then classical machine is optimizing your result, optimizing your parameters. You're getting a new vector of parameters, and then you insert them back. It's such a loop, and then you recalculate everything again and again and again until you won't get the target precision or some results that you are actually seeking for. And so the target is to calculate the derivative somehow using the results of your quantum circuit. And the ideal dream is to calculate this derivative just using the results of the circuit, not using any other stuff, basically. So something that would ideally look like some linear combination of the results of the work of your quantum circuit.
So you mean to make a next step for in parameter space, we need derivative?
Yes, we need some optimization. I mean, some optimization algorithm is happening here that normally is using the derivatives of your functions. Basically, you find the minimum. So you need this derivative somehow, but quantum circuits are not able to calculate the derivatives. They are just giving you mean values of some operators, but not the derivatives itself. So you need to somehow calculate them. So a bit of formalization. So we have a quantum state in the Hilbert space. We have a unitary evolution that is defined by Hamiltonian, the time of your evolution. We say that we know the eigenvalues of the Hamiltonian. For now, we know them precisely. That means that we know the eigenvalues of the unitary evolution. So we say that if we are measuring the observable C, then the result, the mean value of this measurable observable after some time t is defined by this function. This is basically a notation that this mean value is called f from t. So the longer you evolve, the different stuff you get, basically. The question is, what is the derivative f of t? And you want to use only some values of your function in different moments of time. That's everything what you have. What can you do? You can use some classical approximation algorithms. The first thing is to use finite differences. This would be approximation of your derivative. Typically, it's used in many methods. The problem is that then you don't know how many times you need to measure. If your function is not smooth enough, this would be very bad approximation. Like there are a lot of problems basically with finite differences. We also used with my colleagues a method that's called robust polynomial interpolation technique. It's pretty good, it works pretty nice, but for local Hamiltonian evolution under specific conditions. So the big point of all these methods is, first of all, they are approximate. So you are approximating your derivative. It's not equal, like not strict equality. Second, you cannot create any gate set that will give you the derivative itself. So you always need to do a lot of shots of your measurements and then interpolate your derivative somehow by this amount of shots. So again, what we want to create is a rule of calculating the derivative exactly using the results of the measurements of your quantum circuit. And the answer was given, it was inspired by signal processing. So first of all, we introduce the positive unique differences set. So you take all the eigenvalues, you construct the differences of them, and the set of all the unique differences is called omega. And the first parameter shift was introduced for the simplest system, the two-level system. So your Hamiltonian have two eigenvalues, lambda 1, lambda 2. Then the distance is only one distance, omega. And then the derivative is exactly equal to this expression. So you need to measure your observable, basically, you need to estimate your observable twice. I mean, of course, it's done statistically, but you need only 2 points of time where you will measure your observable. And this is basically a constant. So the strength of this method is that it's a strict equality. It's not approximation, comparable to everything else what we ever had before. The question is how to select the shift. Like nobody's giving this answer. Most of the time it's just something between 0 and pi. Like, is there any optimal selection? What is happening when you have more than 2 eigenvalues, right? So it won't work. Yeah.
Very quickly. So under the sign, there is something having the dimensional frequency that multiplied to angle, right? So it shouldn't be there time.
No, you will get a number. That's it.
But it must be dimensionless, right? Inside sinus.
No, it will be fine because this would be just some number. Here would be some angle. What you can take the sinus from an angle. What's the problem?
Says, on the left hand side, we have time derivative.
So omega is frequency,
which
right?
means omega have dimensions of.
You mean that the problem is that this is not dynamical?
Inside sinus.
I think that actually it will be somehow solved here in this part.
Time is dimensionless.
But in principle, how to say, since it comes from signal processing, maybe somehow they are fixing this. This is even not physical in some sense. So I will show you mine, it will be fine there. So this what was introduced for multi-level structure. So if your Hamiltonian has n eigenvalues, so do they have this problem here? No, I think they don't. Yeah, number, everything is fine. So this was already done by physicists. So it's fine. It was introduced in 2022. It was called generalized parameter shift. So or general parameter shift. And here you can calculate the first and the second derivative automatically. You don't need extra measurements. You can calculate them both, having the same collection of measurements. You need 2n-1 values of your function to get the exact solution. Authors selected the phases equidistant. They never explained why they did it. They told that this is reasonable. This was only one sentence. This is a reasonable choice. Later, I will explain actually that this was not just reasonable choice. This was the only choice they could make. And this is a very specific solution. And this is a, what to say, a special case of the methods that I introduce. So it's not general parameter shift rule. It's a very special case, actually. But anyway,
I also have a question. Why do we estimate on this derivative only at 0 time?
They wanted to do like this. This is their in their paper.
But in case of non-zero time, something different in expression from the right hand side.
I think that here would be t plus this, and then here would be t,
okay.
and so on. So they just brought everything to 0. I actually didn't do it, so it would be fine. It will be dependent from t. So the questions are how to select the optimal phase shifts. Because we can see that nobody actually specifies this choice. They just say reasonable. What does it mean reasonable? It's not mathematical. Second is we have different structures of eigenvalues for different Hamiltonians, and parameter shift, the one that is called general, is not taking into account the differences of the structures, because you can have a Hamiltonian with equidistant eigenvalues, or you can have absolutely random eigenvalues, and they want to say that this is absolutely the same for them. That's not true. For example, here the problem can become ill-posed because you have not many unique differences. These differences are all the same. These differences are also the same. So that means that you will get a singularity somewhere while solving your system of equations to get the parameter shift rule. So what we wanted to do is to take into account the different structures of Hamiltonians. This is the first thing. And second, to optimize the selection of phase shifts. So we introduced the following parameter shift rule. It's a very simple idea that we want to find the set of vector B, the vector B such that this will be true. This vector of solutions is dependent from the choice of your shift parameters. So the question is how to select shift parameters, how to solve this equation. We showed in the paper that this problem can be rewritten. It's just equivalent to the following operator equation. They're just the same. So this is still the vector that we want to find. This is a matrix that is constructed from the vectors that look like this. So it's such vectors. So the first row would be from ones, and the second row would be from the distance between lambda 1 minus lambda 2. Then it would be conjugated, then lambda 1 minus lambda 3, and all the different combinations. The size of this matrix would be m by m, where m is all the pairs of the eigenvalues, like all the distances that you have. And mu is the m vector of elements where all the distances are written again. So you have this operator equation, and if you solve it, then you find vector B, and then you have your parameter shift rule. What problems can happen? First of all, if you ever try to solve the operator equations, you know that sometimes they are not well posed by Adamar. That means that the solution, like what is well posed? The solution must, first of all, exist, it must be unique, and it must be stable. So most of the time, the problem is stability, of course. Because, for example, your matrix is not exact, but you get it from the measurement results. So they are random, they are distributed according to some distribution. That means that this matrix is a bit dragging. And then when you are inverting it, the solution may change pretty dramatically. So that means that your system is not robust to small perturbations. In this case, the problem is called ill-posed. Or it can be actually very straightforward problem. This matrix can be singular. That's it. So the solution exists, but you can't find it by simply inverting your matrix. So that's why I divided the cases in this paper into two main ones, well and ill-posed problems. This was done for the first time. And let's say we have a well-posed problem. That means that everything is stable, the solution is unique, the system is solvable, matrix is non-singular. And then the following theorem was proven. It's actually, this result is known from linear algebra. I just made it suitable for the derivative estimation and actually made it just a bit more complicated because here we can also calculate the piece derivative automatically. And this is the strength of this result. So let's say that n is a number of distinct, not equidistant eigenvalues of your Hamiltonian. You have a vector of shifts. M is, as I told, all the unique distances between eigenvalues. This condition ensures that the matrix is not singular, the one that I want to invert. And then it's just known that the parameter shift rule holds if and only if the vector B is the following. This is a determinant. So this is I think it's from Van der Monde matrix. I think it's called like this. So basically, you take the determinant, you take the matrix, you cross the column of interest of x, you substitute the derivatives, and you find the determinant. That's it. So we also generalized it to the case of the superposition of the derivatives. So using absolutely the same functions, you can also get superpositions. This is the first parameter shift rule that gives you so many different derivatives and so many different combinations, and you even don't need to do extra quantum measurements. That's nice. The only complication, but it's a classical complication, is to calculate this. For big matrices, it can be a problem, but up to 20, I think it's still fine. So how to find the optimal shifts? We find them in view of minimization of the variance of the estimate of the derivative. So we just calculate the variance. We say that the variance of every function is not dependent on the moment of time, of the length of the evolution. In principle, it can be different, but here we say that this is the same. We also say that phi's are not random and so on, so they're not random variables. That's why they are serving as a constant. So solving the minimization problem of this equation, we can find the vector of phi's. And this is, of course, done numerically. In the paper, I've done a couple of examples. You can find it doable. So what's happening when the problem is ill-posed?
But what about some examples, for example, for equidistant?
We are coming there because equidistant is ill-posed. It's actually, I would say, the more irregular your structure is, the more well-posed it is. It's maybe counterintuitive. So we are coming to ill-posed problems. So solution may not exist, may not be unique, or maybe not be stable. So we want to find some conditions on shifts and eigenvalues that will ensure us some solution.
If the EM is the matrix, so you mean energy actually have off diagonal.
So EM may not be, just maybe singular. Yes. Or as I told, if there are some parameters inside, like in the beginning, I told that we know the eigenvalues precisely, but normally we have the set of eigenvalues that was estimated somehow, or it's corrupted by noise, because in practice you create a Hamiltonian that is different from the theoretical one. So it can be, the eigenvalues can be a bit different from the ones that you expect. So that means that your E can be also different. And because of this, this changes, the inverted matrix can significantly change your solution. This can happen. I will show this case.
So E must be singular.
How to say? I will show you all the cases. What can you do with this with all the problems? So first, very nice case is equidistant eigenvalues. So here we say that we have eigenvalues, so all the distances are the same. So what does it mean? That actually you have the set of your unique distances is smaller than the amount of all distances. That means that the matrix E is singular because it has just the same rows. They're just the same because this delta is the same for this part. These two delta, like 3 delta. So you will have a lot of
matrix E consists of rows where we have phase factors like exponent I and delta between levels.
Yes, yes.
Delta.
So you will have.
And if we have all the same distances between each neighboring levels, then all rows have the same weight.
Some of them have the same line space.
And this is problem.
This is a problem because then your matrix is becoming singular, and this is a classical example of ill-posed problem. So what to do with it? What you can do? How to say? How we came to this case? We were actually thinking how to solve this problem, even not when it's ill-posed or well-posed, but how to do it easily, I would say, for any size of your problem. And we were thinking that there is a class of matrices that have unitary, they're called unitary by rows or by columns. They are orthonormal. This class of matrices have very nice property. Their inverted matrix is just their complex conjugate. And this would actually really decrease the calculations. So we were thinking, okay, what other conditions on the vectors that are forming this matrix that it will become orthonormal? And suddenly, while writing these conditions and solving, it actually brings me to a Dirichlet, no problem. I found out that the only solution is when the problem is equidistant. That's how nature works, apparently. So what we can do is we say, let's exclude all the similar rows and decrease the size of the problem to 2n minus 1 of unique distances. This matrix is smaller by size, but it's not singular. So now we can solve this problem because it's becoming well-posed. And luckily, we even don't need to invert the matrix. We can just use the orthonormality condition. So the solution was really easy to get. We basically wrote this. And what we got is that the vector of B's is just this vector. And the phi's that are giving the orthonormality condition are equidistant. You remember I was talking about the generalized phase shift rule that was introduced by people in 2022. This is exactly this case. So their generalized phase shift is the only one case equidistant eigenvalues of the Hamiltonian. So this solution is not just reasonable, it's only one, unique, and that's why it's optimal. So, and this was nice to find this connection with the literature, but what will happen if we have all equidistant except of one? Let's say everything is equidistant and one is just an outlier. Strange, but in this case, it's like there is no structure at all. Orthogonality condition is breaking, everything is becoming ill-posed again because you have a lot of similar distances in this case. You cannot use your nice solution at all. So it's really ill-posed problem and you have no clues how to do it. So that means that even one outlier is breaking the structure. So orthogonality property of this matrix is only for equidistant eigenvalue structure and nothing else. So the second thing that we wanted to do is to bring a bit of noise to the stage. So we say, okay, we have another set of eigenvalues. So the black one are equidistant one for which we know the solution exactly. So now we have another set that is a bit shifted, not equidistant, just around these equidistant positions. We say that it's shifted, but not more than on epsilon. So basically it means that this shift from the ideal position is bounded by epsilon. The question is, can we use the solution for the equidistant one as a good approximation of the new set that is more realistic? Because most of the time we will actually get something like this in our real life. So two answers. If this epsilon is comparable to delta, then it's absolutely disconnected sets. Of course, because it's not perturbation. This is just a different set that's completely not equidistant If it's well-posed problem, we use the solution that we showed in the beginning. If it's ill-posed, I will show how to deal with it. If epsilon is much smaller than delta, then we say that the new set is the epsilon perturbation of the equidistant one. And for this case, I proved that if you select epsilon that converges with this speed, it's dependent from two parameters, then the distance between the solution for this not equidistant set, but very close to equidistant, is distant from the ideal case, just like O big from, again, this n power 5b minus 1 to power 5 lambda n. So this is proven. And just a bit to illustrate how it works, the plot. So if you select different alpha and beta, you get different epsilons. So of course, the smaller your alpha and beta are, the bigger epsilon you can tolerate. So your system is getting more robust to the noise, but the distance is also increasing. So we see that if the size of the system is growing, then it's actually not so important anymore, because then the small draggings of lambdas are not inserting you too much noise in the structure. But for smaller systems, it's actually pretty important. So you can select your, like, choose your poison. I don't know, if your experimentalists want your method to be robust to some level of noise, you can show them what errors they can expect. So then there were two other cases. This case is unifying the perturbation one. In this case, I say I have the whole collection of such lambdas. Like, I don't know, experimentalists brought me a lot of different Hamiltonians, and eigenvalues of them were forming such clusters around the equidistant position. And then I want to find the solution, I want to find the distance between the, how to say, the ideal solution and the real life approximation, let's say. So to solve this problem, we again use the previous one with perturbation. So this is just given in the paper. I decided it's not really interesting. But the last and the worst case is you don't have any structure, like it's some eigenvalues, and the problem is, well, like, is ill-posed. So worst scenario, this problem still can be solved.
Why in this case it is ill-posed?
Because first of all, it can be very close distances. So you will get again the matrix that is close to be singular. So that means that the stability can be, how to say, violated. Or, as I will tell later, maybe you don't know these matrices exactly. So the noise of the measurement can actually make your solution unstable. So what does it mean? That, for example, we don't, yeah, as I told you, so the functions that we don't know those operators precisely, we know some approximations of them. And then, if you know the approximations, then you say, okay, that means that the differences between the ideal case and your approximation is, for example, bounded by T and delta, yes, but due to the sensitivity of your solution, this vector will change significantly with the change of this approximation. So just a bit of the change will change the inverted matrix very big, in a big way. So that means that this solution will react on small changes of the parameters significantly. And in this case, we say that this approximation is not reliable. And this is absolutely typical problem in solving such type of equations. To fix this, people use Tikhonov regularization. Just in this paper, I used its stochastic version. So to solve this ill-posed problem with no structure, with how to say, there is an ill-posedness because of any type of problems, because of statistical problems, because singularity and so on. So we need to use the regularization method. And what is it? So the function that we need to minimize is the following. It is called the regularization function. It's dependent from the regularization parameter. That would be the one that will tune this function. The solution of this problem, the B, would be the solution, the good approximation of our problem, and it's proven that it's tending to the true solution with probability 1. This function is called stabilizer functional. It can be selected. It's this is some sort of our freedom to select. And in the case of Hilbert spaces, normally people are selecting the stabilizer functional like this, and the solution is just getting a very simple form. So we take our original matrices, we add this regularization parameter multiplied on a matrix of 1, then approximate inversion is done. So you cannot invert this matrix, you can do it only approximately. You calculate this, is easy to calculate, and this solution is tending to the true one. This is just proven, not by me. I just used this result, proven in 70s actually, so it's super classical. To find these parameters, there are a lot of different methods. The most popular now is a mismatch method. So you determine your regularization number by solving the system of equation, so inequalities even.
Wait, but where is here dependence of place?
This is inside, it will be here. So you will find this solution, then you will substitute it in your parameter shift, and then from minimizing the variance, you're finding the phase. So it's multi-stage process. I understand it sounds pretty hard, but ill-posed problem cannot be easy, and most of the time people are just not having any recipe. This recipe is the best you can have, because you know how close the solution would be to the true one. So the conclusions of this talk, in the conclusions, I just want to compare all the cases that we know to show that actually we covered everything. So well-posed problem is easy, you just solve the equation and that's it. For equidistant case that is very popular in quantum physics, we know the solution, and this is what is called generalized phase shift. Suddenly, the most interesting part was perturbation. This is the most interesting for experimentalists, how much how robust is parameter shifter for the noise. This is the most important, and actually I'm now developing this part on my second paper, because apparently there are everything can be even more complicated for different cases. And of course, the sets is just generalization of the perturbation case. And the last one, the last resort, I call it, is when your problem is just ill-posed, you don't know what to do, everything is absolutely bad, you don't have any solution, and regularization can give you a solution that you can use. And you don't need to guess here anything, because when I was asking people around how you're treating these cases, it was very surprising to me, because people say, yeah, we are just making the matrix well defined. I'm like, but how do you do it? They say, we are just adding some small one matrix. I'm like, yeah, but how are you doing this? So I'm just checking, substitute this, substitute that until it won't be inverted. Well, this is not how scientists are doing it. Because if you have a random process, actually, that is generating you these matrices, it won't work. So this is a good way of formalizing.
Scientific way to.
This is a scientific good way to do it, and it will always work. Let's say like this, and you don't need to be a fortune teller to guess these parameters all the time. You can program it. You can use the tools for that. You can prove theorems. You can use this formula for other derivations.
this inverse will not give you a time variance.
Here, everything is well defined. Like you select this parameter in such a way that the inversion will exist.
This parameter is just like what you.
Yes, it is, but you need to find this correctly. And there are methods to do it correctly, not to guess it. Yeah, in principle, if you need to do it once in your life, yeah, I also would not program all the Tikhonov regularization. I would just select this number, right? But this can be also measurement dependent. So if you have the whole statistics, then this will be not a constant anymore. So, and this brought me to the paper that we published in Physical Review A. That was actually, like, I'm very proud it was immediately accepted. I don't know. I think it was the easiest publishing in my life. I was not correcting anything. Maybe nobody understood anything. I don't know. But I was super happy. Yes. And now I'm doing a follow-up of this project. Maybe I will tell what is a follow-up. So as I told, perturbation is extremely important in parameter shift because asking experimentalists, they told me, yeah, parameter shift looks promising. For two-level system, it works very nice. It's very tolerant to noise. But for a Q-trit, it's not working anymore. And I was like, but why? It doesn't feel like it must be so much of a hassle. They say, we don't know. But it's just not working. Like, it's getting absolutely unpredictable different derivatives. They are always different. It's impossible to use. We don't use it. So when people write in the literature that the next generation methods are parameter shift rule, no, apparently they are not, because experimentalists cannot use it. They don't get robust, good results. So either we are lying or we don't know how to use it properly. So I decided to study what is happening in 2- and 3-level systems. Like here, everything is n, I was very high level, and so on. It's correct, but what is exactly happening in qubits, in Q-trits, in couplets, and so on? And even in qubits, there are a lot of problems. So this problem I solved already for qubits. I showed what would be the distance between the solutions, and so on.
Qubits,
I mean the Hamiltonian two-level Hamiltonian.
Lambda 1 and lambda 2.
Yeah.
But n equals to
No,
n.
n is equal to 2.
To 2?
Yeah, just to 2.
I saw that n is number of qubits, but number of levels cannot be
You can select a Hamiltonian with 2 levels.
Okay.
Like this, I call it a qubit, I'm sorry. So you select a Hamiltonian with 2 levels, and you want to find out what is happening when your eigenvalues are, for example, distributed according to some distribution. So this is a typical realistic problem that your measurements would be different all the time. So you want to understand what would be the spread of your solutions a parameter shift rule. There was a lot of stuff to do there. For 3 levels, it's incredible trouble because the amount of differences is increasing dramatically. So the changes are very significant. For 2, it's not so much important. Everything is just moving. 2 is always equidistant in some point. So it's super easy. Still gives trouble. For 3, everything is becoming dramatically harder. So, but I hope I will manage. My big dream is to actually look at similar structure Hamiltonians. So for example, you have a Hamiltonian with the first gap that is similar. So it would be 2 Hamiltonians. This would be similar. Here, everything would be a bit sandwiched, let's say, but in a different way. What would be the difference between the parameter shift rules for them? Because in practical cases, people are approximating.
So you assume that this result is incorrect for.
It's correct.
I mean, incorrect in terms of applications. So you cannot easily find a solution for parameter shift using your scheme. It is impractical.
It's practical. It's practical, but for only this type of perturbation. There are some other types of perturbation.
Yeah, but this is what I mean. So there are in practice there are Hamiltonians which do not follow your assumption.
Of course, this assumption is too easy. let's say like this, it's still too ideal.
Okay.
Basically, this assumption means only one thing, that instead of your, let's say, diagonal Hamiltonian, you get another diagonal Hamiltonian. Meaning that even the change of basis did not happen because of the perturbations. This is this case. It will still work. I proven it, but I didn't write it in this paper because I was not really thinking about this at that moment of time. So it really took me a while to get a bit into this. However, your Hamiltonian can be perturbed not only on the diagonal, it can be perturbed also on non-diagonal terms. They will become not zero and of diagonal terms, and then you will basically your perturbation will change your basis state. And the change would be dramatical. For 3, I already seen it. It's incredibly big change. And like I will think how to handle it, what conditions I can do, and so on. But of course, the target is to unify for n levels, for some specific structures of eigenvalues, for example, for superconducting qubits, for superconductors, the eigenvalues of the Hamiltonian has very specific structures. They, how to say, the distances start to decrease on some percentage to the higher level. So there is a structure. Would be interesting to see how parameter shift rule would work for superconductors. Or for ions, it's mostly Q-trits now, so it's good to solve the problem exactly for Q-trits, and so on and so on. So it looks like, how to say, the problem is still, this problem still have some things to do, let's say like this. So this is a start.
So as far as I understand, conclusion from what you say is that there is no optimal selection rule
Yet.
Yet.
Let's say like this.
It is expected.
But as I told, so if you have a simulator, right? If you are simulating ideal quantum machine, you can use a parameter shift rule.
Mm-hmm.
So for simulation, it's good. If you have a well-posed problem, again, you can solve the problem exactly. It's all happening for ill-posed problems, right?
But usually, for example, I take
all the life is ill-posed. That's true.
1,000 qubits, two-level systems. It is already ill-posed problem.
Yes. Yeah, but you see, before me, nobody even was telling these words: ill-posed, well-posed, structure of the Hamiltonian. No. So it's like I'm probably the first person who decided to dig into these realms. And as I told, I am not, how to say, I'm not optimistic here, but I still think that things can be solved under conditions. I mean, I have done a lot of exact solutions in this paper, and people were very skeptical when we started saying that nothing can be solved exactly. No, it can be, just you need a bit more conditions again, like this. So,
do you have questions?
Yeah.
What is the mathematics behind the phase shifter? So you expand it to the sign function theory?
But again, what mathematics is behind what?
Behind the phase shift rule.
The parameter shift rule. So if you look at your Hamiltonian, first of all, you need to understand what is the structure of your eigenvalues. You construct this matrix E, this one. You look if the matrix is singular or non-singular. So if the problem is well or ill-posed. If it's well-posed,
no, I mean the previous slide, maybe the first two slides.
Here.
Yeah, here.
Well, your quantum machine is just giving you these functions. You substitute this inside, mathematically calculated. That's it.
Oh, I mean, why you can use the same, even the slide before, maybe slide 3.
If you have more eigenvalues, you cannot do it.
So.
Okay, if you have 3, then it's not working. That's it.
So this is based on what kind of theory? So
for 2.
This expansion.
Just for 2.
For
2 eigenvalues.
For 2 eigenvalues.
Yes, but as I told, all these cases are inside of this one.
No,
so they are all.
Why you can expand it in the sign function theory?
You can.
Sign function theory. Why?
No, it's actually done. Like how parameter shift rule is derivated, it's derivated from the Fourier series. So behind these notations are exactly sine cosine functions.
So if you do the Fourier transform to the first derivative of this of the ft, so you will exactly have the eigenvalue you want, right?
The parameter shift rule is exactly proven from what you're talking about.
If
But you don't need
do the
sine and
Fourier
cosine.
transform, and you will have the spectrum in the
Yes, you will get
will-
the sum of sine and cosine functions.
you will
That's what you
exactly
get.
have the eigenvalue, but so this eigenvalue, for example, in your
But you want to substitute something that you've measured from your gates, from your quantum machine.
then you can just measure the intensity, for example, if for the equal space eigenvalue case, and you have the eigenvalue which is delta and 2 delta and 4 delta, 3 delta, like this, and you have different intensity.
Is it optimal?
What do you mean?
You see, what you are saying me is that basically you can do the whole series of the sine and cosine functions. It's exactly this one, just written in a different way.
For the transform to the...
It's just rewritten one. It's inside of this. That's how you derive the parameter shift, exactly like you say it.
And then you can it just directly give you the eigenenergy. Why do you still need to do the for reasons to have the?
But you need to measure something from your quantum device. That's what you want to substitute. Maybe we don't understand each other. I don't know.
Okay, so if you have a board,
but if you want, I can show you the derivation how I can.
If you have a boarding in the MG level, what can you do for this one? You have broadening for the MG level. For example, you press it to some room temperature, let's say. You have broadening to the MG level, right? And how can you deal with this case in this theory?
Well,
by increasing the...
So I told you have some device, you have some type of observable, you just measure the mean value of it. That's it. It's not I mean, we don't specify any architecture, any observable in these derivations.
Okay, let's say FT is your observable, right? And
yeah.
now you have a FT function, and you do the Fourier transform. You become you transform it to F omega, right? Yeah. Then the F omega will just give you the eigenvalue and its intensity. So for
two levels, you are actually getting something that looks like the original function would be sine and the derivative would be cosine. Yes. If you're talking about this.
No.
Yes, I derived.
What do you mean? You can do you can make Fourier transform and what?
You can just have the eigenvalue.
Yeah, but you don't need eigenvalues.
Yeah, and what? This is not so the problem which Liubov trying to solve is how to estimate derivative of function.
I want to find the derivative using the eigenvalues. I know the eigenvalues.
Then the Fourier transform will actually give you the answer you need. So the first derivative will give you just the omega, right? So,
but as I told you, the parameter shift rule is derived from the Fourier transform. It's just the same.
But you can just use Fourier. Why do you still use?
No, but in practice you cannot make a mathematical Fourier transform. It is discrete Fourier transform.
Yeah, discrete.
You make discrete Fourier transform. You know only discrete Fourier frequencies. So it is not eigenvalues like eigenvalues of I mean. So
no, you can. I mean, what you say is how to say. It sounds correct, but you cannot do it on gates. Like this transformation is impossible to do on a quantum machine. Mathematically, yes. Like this. So you see, I even told that traditional mathematical derivative cannot be directly applied to quantum gates. you're losing the unitarity. Otherwise, everybody would do this, you know.
Otherwise, we just can use find a difference. So
I mean,
Fourier transform is not actually finite difference. It's the second. It's a polynomial expansion.
Polynomial interpolation is not working under all conditions, you know. That
Fourier transform is based on this theory.
yeah, but this is approximation. It's again, it would be again approximation.
Different type of.
It's just different. I mean, you can do it. It's not.
But the idea to make the best estimate for derivative. Who told you that discrete Fourier transform gives you the best estimate for derivative?
Well, we don't.
Almost the same. You have the two j minus 1. So you increase the number of j, and this is just exactly you increase the distance in your Fourier transform.
Do you
From a practical point of view, it is not always possible to increase to infinity number of.
Yeah, I agree. I agree.
But if you want to see the derivation of it from the Fourier, I can show you. I mean, it's. I think that we just a bit misunderstand each other, but it's actually very close things.
Oh,
yeah.
Do we have
yeah, I think it's 1 hour exactly. Good.
Then let's finish.
Yeah.
And in the end, I want to give you a present from something. So this is sign, which means that you gave a talk in our center. Yeah.
That's a very cool tradition. Thank you.
Все.